On a clear night, when you step away from the artificial glow of cities and look upward, you encounter a sight that has moved humans since before we learned to speak about the stars. The night sky presents itself as a dome studded with lights, orderly, eternal, comprehensible. This ancient comfort, this sense that the cosmos is somehow knowable and finite, dissolves instantly once we understand what we are actually seeing. Those pinpricks of light are not mere decoration on a celestial sphere. They are suns. Countless suns. Each one a furnace of unimaginable proportions, burning through millions of tons of hydrogen every single second, and yet appearing to us as nothing more than a photon or two reaching our patient eyes across incomprehensible distances. Our own sun occupies a peculiar place in this hierarchy. In the human imagination, it is supreme, the giver of all earthly light and warmth, the body around which all meaningful celestial motion occurs. We have built our mythologies upon its apparent supremacy, our calendars around its rhythms, our physics initially upon the assumption that it occupied the center of everything. And yet, the sun is, by the standards of the cosmos, nothing particularly remarkable. It is a yellow dwarf, a classification that immediately identifies it as belonging to the most common category of stars. It is middle-aged, neither young nor ancient on the timescales we are discussing. Its mass is such that it will eventually expand, cool, and fade into darkness, but not for billions of years yet. In short, our sun is ordinary. But the universe, in its incomprehensible vastness, contains objects that defy the ordinariness we have assigned to our own star. There exist in the cosmos stellar bodies so immense, so monumentally vast, that they challenge our cognitive capacity to grasp scale itself. These are the red supergiants and hypergiant stars, objects that represent the most extreme expression of stellar growth that matter can achieve before it collapses under its own weight or explodes in a final, catastrophic discharge of energy. Among these titans, one star stands out, at least for now, as the largest ever directly detected and measured by human observers, Stephenson 2-18. To speak of this star, as we shall in the pages that follow, is to speak of extremity itself. It is to confront the fact that the universe, for all its apparent order and intelligibility, contains phenomena that seem to exist almost as refutations of our expectations. How can something become so large? What physical processes could possibly generate an object so massive yet so tenuous, so luminous yet so diffuse? And, perhaps most profoundly, what does the existence of such objects tell us about the nature of reality itself, about the laws that govern the distribution of matter and energy across billions of light years of space and time? These are the questions we shall explore. We shall move from the theoretical frameworks that allow us to understand stellar evolution to the observational techniques that permit us to detect these distant objects, to the specific case of Stephenson 2-18 itself. And, perhaps most importantly, we shall allow ourselves to stand in wonder before the sheer scale and majesty of what we are contemplating, a wonder that is not antagonistic to scientific understanding, but rather its proper companion and completion. To understand how a star could possibly grow to the size of Stephenson 2-18, we must first understand how stars work, how they are born, how they age, and what determines the ultimate fate of each individual stellar object. The history of this understanding is itself a remarkable testament to human ingenuity, for we cannot travel to the stars, cannot sample them, cannot conduct experiments upon them. All we can do is observe them, measure the light they emit, and use the laws of physics to infer their properties. That we have succeeded as well as we have in this task speaks to the predictive power of our scientific understanding. A star is, at its most fundamental level, a sphere of gas held together by its own gravitational attraction. The larger the sphere of gas, the greater the weight it bears at its center, and therefore the higher the temperature and pressure in the core. When a cloud of gas contracts under gravity, which is what happens during star formation, it heats up. If the cloud contains enough mass, the temperature at the center will eventually reach the point at which nuclear fusion can occur. Hydrogen nuclei will fuse together, combining into helium, and in the process, releasing enormous quantities of energy in the form of radiation. This outward pressure of radiation, pushing against the inward crush of gravity, creates a balance. The star settles into a state of equilibrium, and for the duration of its main sequence lifetime, the period in which hydrogen fuses into helium, this balance holds. It is a remarkably stable state, one that can persist for billions of years. Our own Sun is currently in this main sequence phase, a phase that it has inhabited for approximately 4.6 billion years, and will remain in for another 5 billion years or so. For most of a star's life, it remains relatively stable in size and luminosity. However, this stability cannot last forever. Stars are creatures of change, and the changes that come at the end of the main sequence are among the most violent transformations that the universe has to offer. The key to understanding what happens at this stage lies in recognizing that a star is constantly burning through its fuel. The hydrogen in the core is being converted into helium, and this is a one-way process. Eventually, and for a star with the mass of our Sun, this takes roughly 10 billion years, the hydrogen begins to run out. The core, now composed primarily of helium, contracts further under gravity. As it contracts, it heats up. If the temperature becomes high enough, helium begins to fuse into carbon and oxygen. This ignition of helium fusion provides a new source of outward pressure, but it also sets in motion a series of changes that fundamentally alter the structure of the star. For massive stars, those containing many times the mass of our Sun, this process unfolds much more rapidly, and the subsequent transformations are far more extreme. A star with 20 times the Sun's mass, for instance, will exhaust its main sequence, hydrogen, in only a few million years. Once that fuel is depleted, the core contracts and heats, and helium fusion begins. When the helium is nearly exhausted, the core contracts and heats again, and carbon fusion commences. This cycle continues, with each new fuel consuming itself in turn, with each contraction making the star's core hotter and more violent. The star expands and contracts, swinging through different configurations, burning through heavier and heavier elements: carbon, neon, magnesium, silicon, iron. With each new stage of fusion, the outer layers of the star become more turbulent, more extended. The star swells. It grows. It expands outward into the space surrounding it. This is how red giants are created. These are stars that have exhausted the hydrogen fuel in their cores and have entered the phase of helium burning and beyond. Their outer atmospheres expand dramatically, cooling as they do. This cooling causes them to glow with a characteristic red light that gives them their name, the longer wavelengths that characterize a cooler object. A red giant can be truly enormous. Our Sun, when it becomes a red giant, will swell to a size that will likely engulf Mercury and Venus, and possibly Earth as well. We can observe red giants in the night sky, the most famous being Betelgeuse, the red supergiant that marks the shoulder of the constellation Orion. But the story does not end with red giants. For very massive stars, even more extreme evolution awaits. A star must reach a certain mass, roughly 8 times the mass of our Sun, in order to eventually produce a red supergiant, the next step up in the hierarchy of stellar size and drama. Red supergiants are among the largest and most luminous objects in the universe. Some of them have radii 500, 600, even 700 times larger than our Sun. This means that if you were to place such a star at the center of our solar system, its surface would extend well beyond the orbit of Jupiter. The sheer physical size of these objects strains credulity. How can something be so large? And yet, there they are, radiating enormous quantities of light into space, burning through their fuel at prodigious rates, living out the final act of their existence in spectacular fashion. The reason that red supergiants can grow so large is related to the particular phase of stellar evolution in which they exist. They are in the throes of fusing carbon, oxygen, silicon, and other elements. Between each stage of fusion, the core contracts, heats up, and ignites the next fuel. But each contraction also causes the outer layers to respond to the change in pressure support from the core. The outer layers expand and cool. The star bloats. Eventually, it contracts again, but the contraction is never quite complete. The star never quite returns to its previous size. Over the course of the star's final million years or so, before it explodes as a supernova, it can grow to astonishing dimensions. This is the regime in which we find the most extreme stars known to humanity, the red supergiants and the hypergiant stars. These are the most luminous, the most extended, and the most massive stars that current models of stellar evolution predict should exist. And yet, even here, at the frontier of stellar extremity, we find that nature has managed to exceed our expectations. The largest stars we know of are genuinely, bewilderingly enormous. Before we can meaningfully discuss the largest star ever discovered, we must address the question of how we actually measure stellar size. This is not, in fact, a trivial problem. Stars are extraordinarily distant objects. The nearest star to us other than the Sun, Proxima Centauri, is more than 4 light-years away. This means that the light we see from it today was emitted 4 years ago, when the star has moved since then, but the light has been traveling through the darkness of space for all that time before reaching us. For a star that is thousands of light-years away, and Stephenson 2-18 is indeed at such distances, the light it emits takes thousands of years to reach Earth. Furthermore, even for the nearest stars, direct telescopic observation of stellar disks is extremely difficult. The stars are so distant that they appear as point sources of light, even through our most powerful telescopes. We cannot simply point a telescope at a star and see a disk and measure its angular diameter the way we would measure the angular diameter of the moon. Rather, we must use indirect methods, each of which has its own limitations and sources of uncertainty. One of the earliest and most powerful indirect methods for measuring the sizes of stars is the use of eclipsing binary systems. When two stars orbit one another, and their orbital plane happens to be aligned with Earth such that they eclipse each other from our perspective, we gain valuable information. As one star passes in front of the other, the light we receive changes. By carefully observing these light curves, the pattern of light changes over time. We can determine the sizes of the two stars because the duration of the eclipse tells us how long it takes for one star to pass in front of the other, which tells us something about their relative sizes and their orbital speeds. This method is reliable and has been used for more than a century to measure stellar radii. Another method involves the use of spectroscopy, the analysis of light broken down into its component wavelengths. By studying the spectrum of a star, we can determine what elements it contains, how hot its surface is, and other physical properties. In particular, the width of spectral lines tells us about the temperature and density of the star's atmosphere. For very large stars with low surface gravities, this can give us information about the star's radius, since for a star of a given mass, the surface gravity is inversely related to the radius squared. A larger star has lower surface gravity than a smaller star of the same mass. But the most powerful modern method for measuring stellar size is interferometry. Interferometry exploits the wave nature of light. When light from 2 points passes through apertures and then recombines, the waves interfere with one another, creating a pattern of bright and dark fringes. By analyzing this interference pattern, it is possible to determine the angular size of the object from which the light originated. When multiple telescopes are used together in an interferometric array, the effective size of the observations can be dramatically increased, allowing for much finer angular resolution than any single telescope could achieve. Stellar interferometry has become increasingly sophisticated over the past few decades. Facilities like the Very Large Telescope Interferometer in Chile and the Chara array in the United States have revolutionized our ability to measure the angular diameters of stars, particularly giant and supergiant stars that are relatively nearby. By measuring the angular diameter of a star and knowing its distance, typically determined using the parallax method, in which the apparent shift in a star's position as Earth orbits the Sun is measured, we can calculate the actual physical size of the star. It is important to recognize that these measurements come with uncertainties. The distance measurement can be uncertain, the angular diameter measurement has limitations in precision, and the definition of the stellar surface itself is somewhat ambiguous. A star does not have a sharp, well-defined edge the way a planet does, but rather a gradient from the dense, hot interior through the tenuous, cool outer atmosphere. Nevertheless, modern measurements have achieved a level of precision that allows us to meaningfully rank stars by size, and to detect subtle changes in stellar properties over time. It is by means of these techniques, particularly stellar interferometry combined with distance measurements from parallax and other methods, that we have been able to identify and measure the largest stars known to exist. And it is through the application of these techniques that we have come to know Stephenson 2-18 as the champion of stellar size, at least as of the time of writing. In the year 2019, a team of astronomers announced the discovery of what appeared to be the largest star ever definitively measured. The star bore the designation Stephenson 2-18, having been identified during a systematic survey of previously known stellar objects. The name follows a particular nomenclature, and #X201c, Stephenson, and #X201d refers to one of the star catalogs in which it appears. The N #X201c, 2 and #X201d indicates that it was the second such catalog the discoverers were examining, and #X201c, 18 and #X201d is simply a sequential number assigned to this particular object within that catalog. Stephenson 2-18 is a red supergiant star located approximately 19,000 light-years away in the constellation of Scutum, in the equatorial region of the Milky Way galaxy. To put this distance in perspective, the light we see from Stephenson 2-18 today was emitted when the most advanced human civilization on Earth was the ancient Egyptian Empire, during the reign of the pharaohs, and the age before writing had spread widely through the ancient world. For 19,000 years, this light has been traveling through the darkness of space, crossing the vast distances between the stars, passing through the dust and gas of the interstellar medium, until at last it arrived in our solar system and was detected by human instruments. Stephenson 2-18 has a radius that is estimated to be approximately 2,150 times the radius of our Sun. To express this in more concrete terms, if the Sun were the size of a grain of sand, Stephenson 2-18 would be a sphere approximately 4.3 meters, about 14 feet, in diameter. If we place Stephenson 2-18 at the center of our solar system, its surface would extend well past the orbit of Jupiter, far beyond the realm of the terrestrial planets, beyond the asteroid belt, and into the region of the gas giants. In fact, it would extend so far that if we could somehow shrink Stephenson 2-18 slightly and position it in our solar system, it would engulf not only Jupiter but also Saturn. The volume of such an object is almost incomprehensibly vast. The mass of Stephenson 2-18 is estimated to be approximately 19 times the mass of the Sun. This seems contradictory at first. How can something be so much larger in size, and yet not be proportionally larger in mass? The answer lies in the fact that Stephenson 2-18, as a red supergiant in the advanced stages of its evolution, has become extremely diffuse. Its density is extraordinarily low. The outer layers of the star are composed of gas that is far less dense than the air we breathe. If one were somehow able to move through this stellar atmosphere, which would be impossible as the temperatures are still immensely high, thousands of degrees, one would not feel any significant resistance from the gas, because the density is so low. The star has expanded so much that all of its material has been spread over an enormous volume, resulting in an average density that is minuscule by terrestrial standards. The luminosity of Stephenson 2 to 18 is astonishing. The star shines with a brightness that is approximately 440,000 times greater than the Sun. This means that although Stephenson 2 to 18 is much cooler than the Sun on its surface, a red supergiant has a surface temperature of only about 3,200 Kelvin, compared to the Sun's 5,800 Kelvin. It is so much larger that the total amount of light energy it radiates is far greater. The star is burning through its fuel at a prodigious rate. If the Sun were replaced by Stephenson 2 to 18, even at its distance, Earth would be burned to a cinder immediately. The equilibrium of our planetary system, maintained by the particular characteristics of our Sun's light and heat, would be utterly destroyed. Stephenson 2 to 18 is nearing the end of its life. Stars of this character, massive, extended red supergiants, are not stable in the long term. Within a cosmically short time, perhaps within the next million years or so, the processes occurring in the core of Stephenson 2 to 18 will reach a point of no return. The iron core will become destabilized. The nuclear burning will accelerate toward a critical point. And then, in a moment of cosmic drama that will outshine entire galaxies for a brief period of time, Stephenson 2 to 18 will explode as a supernova. This explosion will scatter the elements synthesized in the star's core throughout the surrounding space. New stars may eventually form from this material. Planets may orbit those new stars. Life may emerge. And thus does the cycle of stellar creation and destruction continue, turning stars into dust, and dust into stars again. But Stephenson 2 to 18 is not, in fact, the only contender for the title of largest star. In the years since its discovery, other candidates have emerged. The universe seems to contain a population of extraordinarily large red supergiant stars, each pushing the boundaries of what our current theories of stellar evolution predict should be possible. Understanding these objects, and understanding why they are as large as they are, represents a frontier in modern astrophysics. One of the most famous and well-studied of these giant stars is Betelgeuse, the red supergiant that marks the shoulder of the constellation Orion. Betelgeuse is close enough, at a distance of about 700 light-years, and large enough that it has been the subject of intense observational scrutiny. It has a radius of approximately 700 times the Sun's radius, making it substantially smaller than Stephenson 2 to 18, but still an object of tremendous size and astronomical significance. Betelgeuse is so large that it would engulf the orbit of Mars if it were placed at the center of our solar system. It is also one of the brightest stars visible to the naked eye in the Earth's night sky, which speaks to its tremendous luminosity. Betelgeuse is famous among astronomers as a star in the final stages of its evolution, one that is expected to explode as a supernova at any time in cosmological terms, within the next 1,000 years, or the next 100,000 years, or perhaps even sooner. Another notable contender is Antares, which is also a red supergiant, located in the constellation Scorpius. Antares has a radius estimated to be between 700 and 900 solar radii, again placing it in the same general class of objects as Stephenson 2 to 18, but considerably smaller. Like Betelgeuse, Antares is a bright naked-eye star, and has been known to human observers since antiquity. The ancients did not understand, of course, that they were looking at a star of such tremendous proportions. To them, it was simply a star in the sky, perhaps remarkable for its reddish color, but otherwise just one point of light among countless others. Moving further up the size hierarchy, we encounter stars like Cepheid, a red supergiant with a radius approximately 1,650 times that of the Sun. This star is quite distant and cannot be seen with the naked eye, but through telescopes it can be observed. Its size places it among the largest stars known, though not quite at the extreme end of the distribution. There is also Canis Majoris, another red supergiant with a radius estimated to be around 1,420 solar radii. The measurements of these stars are somewhat uncertain. The exact size depends on how the boundary of the star is defined and on the precision of the distance measurements, but they are certainly among the most enormous objects in the universe. But Stephenson 2-18 surpasses all of these. With its estimated radius of approximately 2,150 solar radii, it occupies a place of apparent supremacy in the current census of known stellar sizes. There have been other candidates proposed over the years. Stephenson 2-18 itself was not always recognized as the largest, and there have been debate and discussion within the astronomical community about which stars deserve the title. Some of these debates hinge on the precision of measurements, on the methods used to determine distance, and on the definition of the stellar radius itself. But at this moment in time, by the most careful measurements available, Stephenson 2-18 appears to be the champion. It is worth noting, however, that the title of an #X201c, largest star, and #X201d is somewhat contested and continually subject to revision. As our measuring instruments improve, as our understanding of stellar physics deepens, and as we discover more stars, the rankings can change. A star discovered tomorrow might prove to be larger than Stephenson 2-18. Or, with better measurements, we might revise our understanding of Stephenson 2-18 itself downward. The universe, it seems, is always willing to surprise us, to exceed our expectations and challenge our assumptions. In this sense, the title of an #X201c, largest star, and #X201d is not a permanent crown, but rather a crown that sits uneasily on the head of whichever star currently holds the distinction, always subject to be taken away. At this point, it is worthwhile to pause and consider a deeper question. Why do stars like Stephenson 2-18 exist at all? Why should there be such a thing as a star with a radius of 2,150 solar radii? Our current models of stellar evolution predict the existence of red supergiants, stars in late stages of stellar evolution, having exhausted the hydrogen in their cores and progressed through phases of helium, carbon, and other element fusion. These models predict that such stars should be quite large, perhaps 500 to 1,000 times the size of the Sun. But do they predict that they should be as large as Stephenson 2-18 appears to be? This is, in fact, an active area of research in stellar astrophysics. The existence of ultragiant stars, like Stephenson 2-18, challenges the existing models of stellar evolution in certain respects. The stars appear to be significantly larger than the current models predict they should be. There are several possible explanations for this discrepancy. One possibility is that the measurements are somehow off, that our estimates of the stellar radii are too large. Another possibility is that our models are incomplete, that we are missing some physical process or phenomenon that would allow stars to grow even larger than we have previously suspected. A third possibility is that these ultragiant stars are somewhat unusual in their properties, perhaps in their mass loss rates or their composition, in ways that cause them to expand more than typical red supergiants. The key to understanding how a red supergiant can become so large lies in understanding the nature of stellar structure and the balance of forces within a star. At every point within a star, the outward pressure of the gas, created by thermal motion and radiation pressure, must balance the inward crush of gravity. If the outward pressure is greater than the inward gravitational force, the star will expand. If the inward gravitational force is greater, the star will contract. In equilibrium, these forces balance. In the envelope of a red supergiant like Stephenson 2 to 18, the temperature is relatively cool compared to the core, several thousand Kelvin rather than millions, but the pressure is still substantial. The star's structure in these outer regions is supported by radiation pressure, created by the flood of radiation flowing outward from the hot core. The atmosphere of the star is quite extended, expanding over enormous distances. A critical factor in determining how large a red supergiant can become is the rate at which it loses mass. All stars lose mass to some degree. The Sun, for instance, loses approximately 1 million tons of material per second in the form of the solar wind, though this is merely a whisper compared to the Sun's total mass. But massive stars, and particularly red supergiants, can lose mass at truly prodigious rates. A red supergiant might lose many times the mass of Earth every year. This mass loss occurs in the form of a strong stellar wind, driven by radiation pressure in the star's atmosphere. The radiation from the star is so intense that it pushes against the material in the star's outer layers, accelerating it outward. As a star loses mass, the gravitational force that holds its outer layers becomes weaker. A star with less mass has less gravity, so it is harder to hold material in as tightly. This means that the star can become even more extended. The extended atmosphere becomes more tenuous, and the star swells further. There is a feedback mechanism here. As the star expands, its surface gravity decreases, the outer layers become more susceptible to being blown away by the stellar wind, more mass is lost, the gravitational hold is weakened further, and the star expands even more. This process cannot continue indefinitely. At some point, the star will lose so much mass that it will transition from a red supergiant to a different type of object. Eventually, a star in this phase will undergo core collapse and explode as a supernova, destroying itself in a cataclysmic explosion. The end point of this process marks the end of the star's life as a distinct object. But before that end point is reached, the star can spend a relatively brief period as an ultragiant, as a star of almost incomprehensible proportions, before it passes away. There is also the possibility that some of the largest stars we observe are in binary systems, that they are not single stars, but rather part of a pair of stars orbiting one another. If one star in a binary system is a red supergiant, and the two stars are close enough, material can flow from the red supergiant to its companion. This mass transfer can affect the evolution of both stars. Some theorists have speculated that certain of the extreme ultragiant stars might be in such configurations, and that the mass transfer and the resulting changes in structure might contribute to their exceptional sizes. However, Stephenson 2 to 18 appears to be a single star, not a member of a binary system, so this cannot explain its extraordinary dimensions. Understanding the precise mechanisms that allow stars like Stephenson 2 to 18 to reach their enormous sizes remains an open question in stellar astrophysics. The existence of these objects is, in a very real sense, pushing on the boundaries of our knowledge, forcing us to refine our models and deepen our understanding of how matter and energy behave under the most extreme conditions. To truly appreciate the significance of Stephenson 2 to 18, it is important to place it within the larger context of the cosmos, to understand not just what this star is, but what its existence tells us about the universe as a whole. The question of how large a star can grow is intimately connected to the question of what kinds of objects the universe produces, and what the distribution of those objects tells us about the fundamental processes of creation, evolution, and destruction that govern the cosmos. The universe contains an almost incomprehensibly large number of stars. Our Milky Way galaxy alone contains an estimated 200 to 400 billion stars. This is already a staggering number. If you were to count one star per second, it would take you roughly 6 million years to count them all. Yet the Milky Way is not unique. The observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. The total number of stars visible to our telescopes is on the order of 10 to the power of 24 or more, a septillion stars, if one prefers the naming convention. This is a number so large that the human mind cannot truly grasp it. It exceeds by many orders of magnitude the number of grains of sand on all the beaches of Earth. Among this staggering multitude of stars, there are representatives of every possible type and class. There are tiny white dwarfs, the remnants of stars that have shed their outer layers and left only their ultradense cores. These objects are so compact that a teaspoon of white dwarf material would weigh as much as an elephant. There are neutron stars, the remnants of massive stellar explosions, where matter is compressed to such densities that electrons are forced to merge with protons to form neutrons. A neutron star with a mass of 1 billion tons is compressed to a sphere only about 20 kilometers in diameter. And there are black holes, the ultimate fate of the most massive stars, objects where space and time are so warped that not even light can escape once it crosses the event horizon. But there are also stars like Stephenson 2-18, stars at the other extreme of stellar properties. Whereas white dwarfs, neutron stars, and black holes represent the extreme of compactness and density, red supergiants and ultragiant stars represent the extreme of extensiveness and diffuseness. They are so large, so spread out, that they would seem to be almost the opposite of a neutron star or black hole. And yet, both extremes are equally real, equally important to understanding the fullness of what the universe contains. The existence of Stephenson 2-18 and stars like it tells us that the universe, in its prodigious fertility, is capable of producing objects that challenge our intuitions and exceed our expectations. We live in a universe that is not content to produce objects of merely reasonable proportions. It produces stars that are thousands of times larger than our own sun, that glow with the light of hundreds of thousands of suns, that will eventually explode and scatter their matter across thousands of light years of space. The universe is, in this sense, profligate. It is generous in the extreme. It does not hesitate to push phenomena to their limits. There is a profound lesson here, one that extends beyond astronomy. The universe, taken as a whole, is a place of extremity and exuberance. It produces not just the ordinary and the typical, but also the extraordinary and the exceptional. Life itself, perhaps, owes its existence to this principle that the universe is willing to explore, to its vastness and diversity, every possibility that the laws of physics permit. Stars like Stephenson 2-18 are not aberrations or anomalies in a cosmos of mediocrity. They are expressions of the universe's fundamental creative power. The discovery of Stephenson 2-18 raises an important question. How did we come to identify and measure this star? How did this particular object distinguish itself from the countless other stars in the night sky? The answer involves a combination of systematic survey work, archival analysis, and the application of modern observational techniques. Stephenson 2-18 was not discovered as a new object that had suddenly come into view. Rather, it was identified in existing catalogs, databases of known stars that had been compiled over many years by various astronomical surveys. The star had been observed before by various telescopes and instruments, but had not been systematically analyzed to determine its size and distance. The identification of Stephenson 2-18 as the largest known star involved going through existing data, applying new analysis techniques, and making careful measurements using the best available observational tools. The method used to determine Stephenson 2-18 size involved stellar interferometry combined with spectroscopic analysis and distance measurements. By analyzing the spectrum of the star, astronomers could determine its surface temperature and other properties. By using stellar interferometry, they could measure the angular diameter of the star as seen from Earth, how large an angle the star subtends in the sky from our perspective. And by measuring the parallax of the star, the apparent shift in its position as Earth orbits the Sun, they could determine its distance. Once these three pieces of information are available, the angular diameter of the star, its distance from Earth, and some understanding of how the angular diameter relates to the physical radius, which depends on how we define the stellar surface, it is possible to calculate the actual physical radius of the star. For Stephenson 2-18, these calculations yielded a radius of approximately 2,150 solar radii, placing it at the extreme end of the size distribution for known stars. It is worth noting that this measurement, like all astronomical measurements, comes with uncertainties. The radius of Stephenson 2-18 might be as low as about 2,000 solar radii or as high as about 2,300 solar radii, depending on the particular methods and assumptions used. But even with these uncertainties, the star is clearly exceptional, far larger than the vast majority of known stars. It is in the category of the ultra-giant stars, the most extended objects known to science. The story of Stephenson 2-18 is, in many ways, a representative example of how modern astronomy works. We do not discover the secrets of the universe through sudden, dramatic revelations, but rather through patient, systematic observation combined with careful analysis and the application of mathematical models. We gather data across many wavelengths of light, visible light, infrared, radio waves, using multiple instruments and techniques. We compile this data into catalogs and databases. We apply increasingly sophisticated analysis methods. And gradually, the universe reveals its secrets. The discovery of Stephenson 2-18 and the careful measurement of its properties represents not a sudden breakthrough but rather a culmination of many decades of work by many astronomers and many institutions, all contributing to the gradual expansion of human knowledge about the cosmos. It represents, in a sense, the triumph of the scientific method, the idea that by careful observation, by precise measurement, by honest evaluation of evidence and honest acknowledgement of uncertainty, we can come to understand even the most distant and exotic objects in the universe. Stephenson 2-18 is not an eternal object. Stars do not endure forever. They are born from clouds of gas and dust. They live their lives in various configurations and stages of evolution, and ultimately they die. For a star like Stephenson 2-18, the end is not far away by cosmic standards. The star is in the final chapter of its existence, racing through the last phases of nuclear fusion in its core. The nuclear processes occurring in the core of Stephenson 2-18 are in their final stages. The star has already burned through hydrogen and helium, and is now fusing heavier elements, carbon, oxygen, silicon, and others. Each stage of fusion proceeds at an accelerating pace. The helium in the core of a red supergiant like Stephenson 2-18 is burned up in a few million years, whereas the hydrogen in the core of a main sequence star like our Sun lasts for billions of years. The later stages of fusion occur even more rapidly. Eventually, the core of Stephenson 2-18 will become largely composed of iron. Iron is the endpoint of nuclear fusion that releases energy. Fusing iron requires energy rather than releasing it. At this point, the core can no longer be supported by radiation pressure from nuclear burning. The core becomes unstable. It collapses catastrophically. In a fraction of a second, the entire core of the star, containing the mass of roughly 20 suns, is compressed from a size comparable to that of Earth to a size smaller than a mountain, and then smaller still. The collapse is halted only when the density becomes so extreme that the pressure of degenerate matter compressed beyond the point where further compression is possible, can provide support. A core bounce occurs, and a shockwave propagates outward through the star. This shockwave will blow the star apart. The outer layers of Stephenson 2-18, which encompass so much space and contain so much material, will be accelerated outward at speeds of 30,000 kilometers per second or more. The explosion will be almost incomprehensibly violent. For a period of weeks or months, Stephenson 2 to 18 will outshine entire galaxies. The light from the supernova explosion will travel outward in all directions, including toward Earth, and when it arrives, thousands of years from now, it will be visible from Earth, even in the presence of sunlight, as a bright point of light in the daytime sky. The material ejected from the supernova explosion of Stephenson 2 to 18 will eventually slow down and cool. The hot gas and plasma will gradually merge with the interstellar medium, the gas and dust between the stars. Over thousands and millions of years, this material will mix with the surrounding gas and dust, enriching it with the heavy elements synthesized in the star's core. New clouds of gas will form from this enriched material. New stars will be born. Some of these new stars will have planetary systems. And perhaps, on some of those planets, life will emerge. And thus the cycle continues. Stars are born from the ashes of their predecessors, living their lives and eventually returning their matter to the cosmos, to be recycled into new stars and new worlds. This is the ultimate fate that awaits Stephenson 2 to 18, not in the near future, perhaps not for another 100,000 years or more, but inevitably. The extraordinary star that holds the title of the largest known star in the universe is in the process of transforming, undergoing the final chapters of its existence. And when it does transform, when it does explode, the universe will witness a cataclysm, a spectacular exhibition of the awesome power of stellar death. The existence of Stephenson 2 to 18 and of other ultra-giant stars raises a question that extends beyond astronomy into theoretical physics. Is there an upper limit to how large a star can grow? Is there some physical principle that sets a maximum size? Or can stars, in principle, grow indefinitely, limited only by the amount of material available to them? The current understanding is that there are indeed limits, though these limits are not as strict as one might initially expect. One major constraint is that a star must have sufficient mass to support itself against gravitational collapse. A star must be massive enough that the temperature and pressure in its interior are high enough to sustain nuclear fusion, at least at some point in its life. Stars with masses less than about 0.08 solar masses will never reach the temperature required for hydrogen fusion, and will instead become brown dwarfs, objects that are somewhat star-like, but do not qualify as true stars because they never undergo nuclear burning. However, for stars above this minimum mass, there is no corresponding maximum. There is no hard ceiling above which stars cannot exist. Very massive stars, those with masses of 100, 200, or even 300 solar masses, appear to exist in nature, though they are rare. Such massive stars burn their fuel rapidly, live short lives measured in millions of years rather than billions, and end their existences in cataclysmic supernovae. At the high mass end, there are theoretical limits imposed by the extreme radiation pressure in the stellar interior. If a star becomes too massive, the radiation pressure in its core becomes so extreme that it can overcome the binding effect of gravity, and the star simply blows itself apart in what is sometimes called a parinstability supernova or photodisintegration supernova. This process is thought to occur in stars above about 140 solar masses, or perhaps higher, depending on the star's composition and other factors. Thus, there is an upper limit on stellar mass, though the exact location of this limit is an active area of theoretical research. But the limits on stellar size are somewhat different from the limits on stellar mass. A star's size depends not just on its mass, but also on its evolutionary state. A star with a given mass will be relatively compact while bearing hydrogen in its core, larger as it becomes a red giant, and even larger if it becomes a red supergiant. The size is determined by the balance between the outward pressure from nuclear burning and radiation, and the inward crush of gravity. As a star loses mass through stellar winds, its surface gravity decreases, and it can expand even further. For red supergiants, there appear to be practical, though not absolute, limits on size. The most massive red supergiants, with initial masses above about 40 solar masses, will undergo core collapse and explode as supernovae before they can expand to the most extreme sizes. Red supergiants with slightly lower initial masses can grow larger, because they have more time in the red supergiant phase before they explode. But eventually, all red supergiants will reach a point where the balance of forces in their interiors becomes unstable, and they will undergo core collapse and supernova explosion. Stephenson 2-18, with its radius of 2,150 solar radii, represents the current observational record for stellar size. But it is likely not the absolute limit. Theoretical models suggest that stars could potentially grow somewhat larger, perhaps to radii of 2,500 or 3,000 solar radii, if conditions were right. But such extreme sizes are probably rare, because they require a particular combination of mass, composition, and evolutionary timing to achieve. Most red supergiants remain somewhat smaller. The question of stellar size limits is not merely an abstract theoretical question. It connects to fundamental issues in stellar astrophysics. What determines the structure of a star? How do radiation and gravity interact to shape stellar configurations? What happens at the extremes of the parameter space that nature explores? By studying objects like Stephenson 2-18, objects that push on the boundaries of what we thought was possible, we improve our understanding of these fundamental questions. To stand before the facts of Stephenson 2-18 and contemplate them seriously is to encounter, in a very visceral way, the strangeness of our universe. We live on a small planet orbiting an ordinary star. Our star is one of hundreds of billions in our galaxy. Our galaxy is one of hundreds of billions in the universe. And within this almost incomprehensibly vast cosmos, there exist objects like Stephenson 2-18, stars so enormously large that the human mind struggles to process what is being claimed about them. What does it mean to say that Stephenson 2-18 has a radius of 2,150 solar radii? We have offered some comparisons. If the Sun were a grain of sand, Stephenson 2-18 would be a sphere about 14 feet in diameter. If Stephenson 2-18 were placed at the center of our solar system, its surface would extend far beyond Jupiter. These comparisons are useful, but they do not quite convey the full strangeness of what we are discussing. There is something about the sheer numerical scale of these objects that exceeds our normal capacity for geometric visualization. The volume of Stephenson 2-18 is so vast that it is difficult to express in familiar terms. The volume of a sphere is proportional to the cube of its radius. If Stephenson 2-18 has a radius 2,150 times that of the Sun, then its volume is roughly 2,150 cubed. That is, roughly 10 billion times the volume of the Sun. To put this in perspective, if you could somehow hollow out Stephenson 2-18 and fill it with Earths, you could fit roughly 5 billion Earths inside. If you line up Earths along the diameter of Stephenson 2-18, you would need about 4,300 Earths to stretch across. And yet, despite this enormous volume, Stephenson 2-18 is not particularly massive. It contains only about 19 solar masses of material. This means that the average density of Stephenson 2-18 is extraordinarily low. The density is roughly 10 billion times lower than the density of water. In fact, Stephenson 2-18 is so diffuse that it is less dense than many gases at Earth's surface. If you were somehow able to exist in the outer layers of Stephenson 2-18 without being destroyed by the intense heat, you would not encounter the resistance of a dense solid or even a dense gas. You would move through a medium so rarefied that it would be difficult to perceive as anything but nearly empty space. This combination of enormous size, with relatively low mass and density, is one of the most striking features of stars, like Stephenson 2 to 18. It reveals something profound about the nature of gravity and structure. The gravity holding Stephenson 2 to 18 together is quite weak. A spacecraft could, in principle, escape from the surface of such a star with a speed slower than a jet airplane. And yet, gravity still holds the star together. Gravity, the weakest of all fundamental forces on atomic scales, nonetheless holds sway over objects of such tremendous size that they dwarf our imagination. In a sense, Stephenson 2 to 18 is an illustration of gravity's dominion. No matter how large an object becomes, gravity continues to shape its structure. To contemplate Stephenson 2 to 18 is also to contemplate the nature of light and energy. This star, despite its low density and low surface temperature, shines with a brightness 440,000 times greater than the Sun. It does so because of its enormous size. Every square meter of the star's surface, though cooler than the Sun's surface, radiates energy. And because the star has such an enormous surface area, the total energy radiated is tremendous. If this star were placed at the distance of the Sun, it would deliver about 440,000 times as much energy to Earth as the actual Sun does. Life as we know it could not exist in such a world. In all of these ways, Stephenson 2 to 18 is a challenge to our understanding, a limit case that tests the boundaries of what we thought was possible. It is also a source of profound wonder. When we look upon the facts of this star, its size, its brightness, its position in our galaxy, we are confronted with the grandeur and exuberance of the physical universe. We are reminded that we live in a cosmos that is not merely large but truly immense, not merely diverse but genuinely alien to our everyday experience. The discovery and careful measurement of Stephenson 2 to 18 represents not a conclusion, but a step on a longer journey of discovery. The future of stellar astronomy holds the promise of identifying even more extreme objects, of refining our measurements of existing objects, and of deepening our theoretical understanding of how stars work. New technologies and observational techniques are being developed that will allow astronomers to see further into space and to measure stellar properties with greater precision than ever before. One particularly promising approach involves the use of space-based interferometry. Currently, the most powerful stellar interferometric facilities are based on Earth, limited by the Earth's atmosphere and the need to use Earth-based observing locations. But future space-based observatories, with multiple instruments flying in formation in space and communicating with each other, could achieve angular resolution far superior to anything available today. These facilities would be able to measure the diameters of distant stars with unprecedented precision, and to study the structure and evolution of stellar atmospheres in detail that is simply not possible today. Improvements in our theoretical understanding of stellar evolution are also anticipated. Current models of stellar evolution, while quite sophisticated, have limitations. They do not always perfectly predict the observed properties of stars. By comparing detailed observations of real stars with theoretical models, and by iteratively refining the models to better match the observations, astrophysicists hope to arrive at increasingly accurate descriptions of how stars work. This process is expected to continue for many years. There is also the possibility that new statistical techniques and machine learning algorithms could be applied to the enormous catalogs of stellar data that modern surveys have generated. These techniques might reveal patterns in the data that human analysis has missed, or might identify peculiar objects worthy of follow-up observation. The automated survey facilities that are continuously scanning the sky could potentially discover new stellar giants. It is entirely possible that a star larger than Stephenson 2 to 18 will be discovered and properly measured in the coming years or decades. The title of an #X201c, largest known star, and #X201d, is not a permanent crown, but rather a prize that goes to whichever star currently holds the distinction. The universe may well have other surprises in store. But whether or not Stephenson 2-18 retains its title, the significance of this star is not diminished. It remains one of the most remarkable stellar objects known, a limit case that illuminates the extremes of stellar existence. In a broader sense, the study of extreme objects like Stephenson 2-18 is valuable not just for its own sake, but because it challenges our theoretical frameworks and forces us to think more carefully about the principles that govern stellar structure and evolution. Science advances not just through the steady accumulation of observations, but through encounters with phenomena that surprise us, that do not fit our expectations, that push us to revise our understanding. Stephenson 2-18 is precisely such an object. It is a gift to science, a puzzle to be solved, a window into the deepest workings of the cosmos. We began this inquiry with a question: how can something become so large? How can a single object, held together by nothing more than its own gravity, expand to the proportions of Stephenson 2-18? Through the course of our exploration, we have traced the path by which stars grow and evolve, by which they progress through stages of increasing size and luminosity, by which they approach the limits of what gravity and nuclear burning can maintain. Stephenson 2-18 is the largest star known. At the present moment, in the early decades of the 21st century, after centuries of astronomy and decades of detailed modern study, this is the object that holds that distinction. Its radius is approximately 2,150 times the radius of the Sun. Its luminosity is approximately 440,000 times the luminosity of the Sun. It is composed primarily of hydrogen and helium, with smaller quantities of heavier elements. It is located approximately 19,000 light-years away, in a region of the Milky Way that is rich in young, massive stars, and the remnants of stellar explosions. To know about Stephenson 2-18 is to know something profound about the nature of our universe. It is to understand that the cosmos is not a place of modest proportions and quiet stability, but rather a place of extremity and exuberance. It is to recognize that the universe, given the freedom that the laws of physics permit, will explore possibilities that exceed our imagination. In the existence of Stephenson 2-18, we see evidence of this creative power of nature, this willingness to produce objects that are genuinely, almost bewilderingly extreme. When we look up at the night sky, our eyes receive light that has traveled across vast distances of space and time. Most of what we see are ordinary stars, like our own Sun, stars that have passed through their main sequence phase, and are either now in that phase, or are yet to be born. But some of the light we receive comes from more distant regions, from stars that are intrinsically far brighter than those nearby, and thus remain visible despite their distance. And among these distant stars, burning with tremendous luminosity, are objects like Stephenson 2-18, stars in the final stages of their existence, stars that will not endure for billions of years as our Sun will, but rather will burn themselves out in a few million years and end their lives in spectacular supernovae. The light from Stephenson 2-18 that we observe today began its journey toward Earth 19,000 years ago. It has traveled across the interstellar medium, passing through clouds of dust and gas, navigating around massive structures in the galaxy, before arriving at our planet and being detected by human instruments. The same light might be seen by future generations, by observers far more sophisticated than we are, who will have measured even more accurately the properties of this remarkable star, and who will understand its significance even more deeply than we do. And in the end, when Stephenson 2-18 finally explodes, whether that occurs 10,000 years from now or 100,000 years hence, the universe will witness a moment of terrible beauty, a moment when the accumulated matter and energy of this enormous star is released in a blast of radiation and particles that will outshine galaxies. The elements synthesized in the core of Stephenson 2 to 18 will be scattered to the winds, enriching the interstellar medium, seeding the formation of new stars and new worlds. And the cycle will continue. Stars will be born from the remnants of Stephenson 2 to 18. Some of those stars will have planetary systems. And perhaps, on some of those planets, life will emerge, and beings will look up at their night sky and wonder at the stars they see. This is the legacy of Stephenson 2 to 18, and the legacy of all the stellar giants. They are not isolated phenomena, but rather part of the great cycle of creation and destruction that gives meaning and form to the universe. To study the stars is to participate in the oldest of human endeavors. The ancients looked up at the sky and saw patterns, saw stories written in light. Modern astronomy has transformed those ancient observations into rigorous science, has revealed the profound physical principles governing stellar behavior, has shown us that the cosmos is far stranger and more wondrous than the ancients could have imagined. Stephenson 2 to 18 is one expression of this cosmic wonder. It is a star that deserves our contemplation, our study, and our awe. In the presence of such cosmic extremity, we are reminded of our own smallness, our own brief moment in the vast span of cosmic time. The Earth, that small blue world orbiting a yellow dwarf star, is a universe unto itself to those who inhabit it. But placed in the context of the true cosmic landscape, in which giants like Stephenson 2 to 18 roam the darkness between the stars, our world becomes infinitesimally small. And yet, this smallness is not something to be dispirited. Rather, it is a source of wonder, a reminder that we are part of something vastly larger than ourselves, something that we can strive to understand, something that inspires us to look upward and ask the eternal questions. What is out there? How does it all work? What does it all mean? Stephenson 2 to 18 has no answers to these questions. It is simply a star, burning, radiating, nearing the end of its existence. But in its very existence, in its magnitude and majesty, it points towards something beyond itself. It reminds us that we live in a universe governed by natural law, a universe that is noble, a universe that is willing to reveal its secrets to those patient and diligent enough to ask the right questions. This is the greatest gift that the study of the cosmos can offer, not just knowledge about what exists out there, but a sense of participation in something larger than ourselves, something worth dedicating our lives to understanding.